Good evening. Today we are going to be talking about gas laws. And before we actually start to do problems with gas laws, I want to go over a few formulas and constants that we will need to know when doing these gas laws. First of all, I want to note that temperature will always have to be in Kelvin. And I've given the formula here, Kelvin equals degrees Celsius plus 273. Standard temperature and pressure is also something that you may end up dealing with in a problem, although on today's practice worksheet I don't give any problems that are at standard temperature and pressure. But for your information, STP, standard temperature and pressure, is 1 atmosphere or 760 millimeters of mercury, and the temperature that's standard temperature is 273 Kelvin. If you have a gas that is at STP, its volume for 1 mole of gas will be 22.4 liters. This is a useful conversion factor. So you may find this conversion factor very useful in the future. If a problem deals only with volume, pressure, and temperature, then using the combined gas law will be what you will use to solve the problem. So P1V1 over T1 equals P2V2 over T2. That is the combined gas law. If the problem deals with volume, pressure, temperature, and moles or mass, you will be using PV equals nRT. And that is where P is pressure, V is volume, R is the ideal gas constant, and these are the two numbers that are the ideal gas constant. Pay attention to units. N is number of moles, T is the temperature in Kelvin. And the last gas law we want to look at is Dalton's law of partial pressures. And that is a very simple law. It simply says the total pressure of a mixture of gases is the sum of the partial pressures of all gases making up the mixture. Keep it simple. Alright, we're going to solve gas law problems, and we're going to use these rules to help us solve them. The first thing that you do is determine the type of gas law problem. Then write the appropriate gas law equation. Check your units. Make sure that temperature's in Kelvin, and are your pressure and volume units the same? Many times it won't make a difference what they are, it's just that they have to be the same. If one is in atmosphere, the other must be in atmosphere. If one is in milliliters, the other must be in milliliters. If they are not the same, then convert them. If it's not in Kelvin for the temperature, convert it. Then you will simply plug the variables into the equation and solve for the missing variable. Let's get started. A car has an internal volume of 2,600 liters. If the sun heats the air inside the car from a temperature of 20 degrees Celsius to 55 degrees Celsius, what is the pressure? Assume the pressure was initially 760 torr. In this problem, we are given volume one time, but we're not given any other second volume, and to be honest, volume is not important in this problem. What is important is pressure and temperature. Now, whose law deals with pressure and temperature? That's Gay-Lussac's law. So we know that this is a Gay-Lussac equation, but as I've mentioned before in class, we do not memorize each of the individual equations. Instead, we use the combined gas law, and that is P1V1 over T1 equals P2V2 over T2. Now let's look at what's important. Again, volume is not important. So scratch volume out, and it simply becomes P1 over T1 equals P2 over T2. Now let's look at our units. Check the units. 20 degrees Celsius, add 273, that's 293 Kelvin. 55 degrees Celsius, add 273, that is 328 Kelvin. Now we're ready to plug in our variables. Pressure 1 is 760 torr. Temperature 1, 293 Kelvin. Pressure 2, that's what we're looking for. Temperature 2, 328 Kelvin. Now, algebraically, how do we solve the problem? We will bring our 328, since it's being divided on this side, we will multiply both sides by 328. That gets rid of it on the right side. Notice our units now of Kelvin will cancel. Grab your calculator, and you will see it is 328 times 760 divided by 293. And the answer we get is 850.7849, etc. Significant figures go back to original numbers. Notice these are two significant figures. However, it's added. The rule for addition is decimal place or least precise. So these are correct. 3 significant figures for each of these numbers. The givens also had 3 for the torr, and so our final answer will have 3. This is our third significant figure. Does the 7 make the 0 go up? Yes, it does. The answer is 851, and don't forget your unit of torr. 851 torr. In our next problem, it looks like we have volume, temperature, volume, and it wants to know temperature. But notice it's wanting temperature in degrees Fahrenheit. So let's decide whose law deals with volume and temperature. Volume and temperature, that's Charles' law. Again, though, it really doesn't matter if it's Charles' law because we're still using our equation for the combined gas law. What's important, what's not? Pressure is not important. Scratch pressure out. Convert to Kelvin. That is 292 Kelvin. We're looking for temperature, so we only need to convert one time right now. Plug in your variables. Volume 1, 250 milliliters. Over temperature 1, 292 Kelvin. Volume 2, 285 milliliters over temperature 2. Now, many times students find solving for the bottom variable, the denominator, hard. Give you an easy trick to do this. Flip everything. Flip both sides. And so when you do that, basically you're flipping both sides so that T2 is now on top. If you don't have any trouble doing this the standard way, then don't flip it. But if it bothers you to solve for that bottom variable, then flip the equation. Now, once it's flipped, you simply, what's divided, you multiply. So you're going to bring the 285 milliliters to the top. It gets rid of it on that side. Milliliters cancel. Grab your calculator. 285 times 292 divided by 250. We get 332.88 Kelvin. Now, I did tell you in this problem that I want the temperature to be in Fahrenheit. I didn't read this question, but I'm sure you have, so I won't reread it for you. How do we get this into Fahrenheit? Well, that's 332.88 Kelvin minus 273. That will give us 59.88 degrees Celsius. Then we plug that into degree Fahrenheit equals degrees Celsius times 1.8 plus 32. And so if I plug in the 59.88 times 1.8 plus 32. We get 139.784. Rounding that properly, I'm going to round that to the nearest whole number, and we get 140, and we'll go ahead and put the decimal degree Fahrenheit. So our car was very hot. Couple comments I want to make before I move on to any more problems here. Do you realize that you can check yourself on all gas law problems? There's really no reason on earth you should miss a gas law problem. You can check yourself. It's basic algebra. Plug in what you get into the variable. So in other words, what you're going to do, you're going to take 851 TOR and put it on top here. Then you're going to grab your calculator and you're going to take the original numbers, 760 divided by 293, see what you get. It should be the same thing as 851 divided by 328. Same thing would work here. Take your Kelvin temperature that you get, the 332.88, plug it right here. Then do the math. Milliliters divided by Kelvin temperature, milliliters divided by Kelvin temperature, and your answer on each side should be the same. Let's go to the next problem. 4 moles of a gas at a pressure of 5.4 atmosphere, having a volume of 120 liters. What's the temperature? Alright, go back to our original comments at the very top of this paper. What does it say about moles or mass? When are we going to see moles or mass? That is when we have an ideal gas equation problem, and that is PV equals nRT. So this is an ideal gas law. To do the ideal gas law equation, you must know the constant, or the constant must be given to you by your teacher. So go up. These are the constants that we're going to be using. Notice it says pay attention to units. There are two different units for pressure here. What are our units for pressure? They're atmosphere. So that tells us then that we're going to be using the 0.0821 liter atmosphere per mole Kelvin. So let's plug it in. I'm looking for temperature, so I don't have to convert temperature. P is atmosphere, so 5.4 atmosphere times a volume of 120 liters equals 4.0 moles. My gas constant is 0.0821 liter atmosphere per mole Kelvin times temperature. I'm not going to show this math, but I think by now you know what to do. The 4 and the 0.0821 are going to come to the bottom on both sides. You'll get rid of it on the right. So then to do the problem mathematically, we're going to say 5.4 times 120 divided by 4 divided by 0.0821. And the answer I get on the calculator is 1973.20341 Kelvin. Go back and look at significant figures and you can see that the number of significant figures should be 2. 19, does the 7 make the 9 go up? Yes, it does. That would become 2000. That would only be one significant figure. This is an example of a problem that must be put into scientific notation. And the answer is 2.0 times 10 to the third Kelvin. Let's move on. Moving on quickly now, we're looking at partial pressures. It gives us a mixture of gases. Immediately I know that's Dalton's law of partial pressures, which simply means the total pressure is the sum of the partial pressures. So let's go ahead and do that. The pressure total equals the pressure of CO2 plus the pressure of H2S plus the pressure of air. Plug in what we know. Total pressure, 0.99 atmosphere equals pressure of CO2, 0.05 atmosphere, plus H2S is 0.02 atmosphere, plus the pressure of air. Mathematically, folks, you just simply say 0.99 minus 0.05 minus 0.02, and I think that we all can do that in our head. That would be 0.92 atmosphere. So 0.92 atmosphere is the pressure of air. The next problem deals with this problem, and it says, what is the partial pressure of oxygen near a blast furnace if this air contains 22% oxygen? Simply find what is 22% of 0.92 atmosphere. So 22% is the same as 0.22. So then we're going to take our 0.92 atmosphere, which is our pressure of air, times 0.22, which is our percent, that is oxygen, and our answer then will be 0.92 times 0.22, and we get 0.2024. Round that to two significant figures. Does the 2 make the 0 go up? No, it doesn't. So 0.20 atmosphere is the partial pressure for oxygen. All right, the next problem that we're going to deal with is a problem that appears to have all of the variables. We've got volume, we've got temperature, volume, atmosphere, and we're looking for pressure. This is a true combined gas law problem. So we're going to use all the variables in this problem. So let's start off. P1 V1 over T1 equals P2 V2 over T2. Let's go now to our problems with the Kelvin temperature and convert that. 45 plus 273 equals 318 Kelvin. 35 plus 273 will be 308 Kelvin. Now I'm going to plug in. Pressure 1 is 2 atmosphere. Volume 1 is 28 liters. Temperature 1, 318 Kelvin. Pressure 2, I don't know. That's what I'm looking for. Wait a minute. I didn't read the problem right, did I? Tell me what's going on here. If I measure the pressure after the change to be 2 atmosphere, what was the original pressure of the gas? I'm not looking for pressure 2, am I? No, I'm not. I'm looking for pressure 1. So, I purposefully used my erasable pen. So let's erase this. Maybe you caught me before I did this. It's late. So I'm not thinking very straight, am I? Let's go back. Plug in now 2 atmosphere and our second volume, 34 liters, and our 308 Kelvin. Alright, that looks better. And except for one problem. I called that P2. Let's fix that. P1. Alright, let's look now. What are we doing? We're finding P1. So what we want to do is get rid of 28 liters. For those of you that are a little algebra challenged, we're going to divide both sides by 28 liters. Divide both sides by 28 liters. Get rid of it on the left side. When we are dividing to begin with, to get rid of something that's divided, we multiply. Multiply it on this side, multiply it on this side. Now, I'm going to take a chance to look at my units. Kelvin cancels, liters canceled. Grab the calculator, plug in the numbers. Alright, 2 times 34 times 318 divided by 308 divided by 28, and I get on my calculator 2.50742, yada yada. Atmosphere, go back to my original numbers, and it looks like I need two significant figures, so 2.5 atmosphere. Do you remember how to check yourself? You take 2.5 and you plug it right here. Let's do one like that. Real quick, 2.5 times 28 divided by 318. This is 0.22. So this side is 0.22. Let's put it over here. This side is 0.22. Alright, now then, take our 2 times 34 divided by 308, and looky there, you get 0.22. So it checks. Take the time to check yourself, especially on a test, if multiple choice especially. Alright, we're going to the ocean. A balloon filled with 0.235 moles of air. Immediately, as soon as you see moles, your brain should say, you know what, that's probably a PV equals nRT problem. I don't have a balanced equation, so there's nothing I could do with a stoichiometry problem, so it's going to be PV equals nRT. So I've got a balloon filled with 0.235 moles of air. So this is called an ideal gas equation, or ideal gas law. It has a pressure of 95 atmosphere at an ocean depth of 3,117 feet. The temperature at this depth is around 6 degrees Celsius. What is the volume of the balloon? Does it matter how deep I am? No. If you don't want to pay attention to that, cross it out. Alright, let's plug and chug. Pressure, 95 atmosphere. Volume, I don't know. N, 0.235 moles. R, 0.0821 liter atmosphere per mole Kelvin. And temperature, that would be 279 Kelvin. 273 plus 6 would be 279. So 279 Kelvin. Alright, do the math. Divide by 95 atmosphere on both sides. Atmosphere cancel. Kelvin cancels. Mole cancels. There's liters. Calculate. 0.235 times 0.0821 times 279 divided by 95. And on my calculator I get 0.056661963. Significant figures is where you'll mess up on this one if you mess up at all. It has two significant figures. So how do you write 2? Are these my 2? No, they aren't. This 0 is not significant. These are my 2. Go back 1. So my answer is 0.057. What are my units? Liter. Last problem. If we took 2 liters of gas at 1 atmosphere and compressed it to a pressure of 6.00 times 10 to the 4th atmosphere, what is the new volume? Who are we dealing with here? Volume, pressure. Who is that? That's Boyle's law. So P1 V1 over T1 equals P2 V2 over T2. What's not important? Temperature. So pressure 1 atmosphere. Volume 1, 2.00 liters equals 6.00 times 10 to the 4th atmosphere times V2. Divide both sides by the 6 times 10 to the 4th atmosphere. Atmosphere cancels. Grab your calculator. That's 1 times 2 divided by 6 exponent 4 equals, and you get 0.0000. Double check. 1, 2, 3, 4 zeros, yes? 3, 3, 3, 3 repeating. Now, obviously, you're not going to write the answer that way. So how would we write it? Let's put it in scientific notation. It needs 3 significant digits. Those are my 3. If you recall how to put this in scientific notation on your calculator, here is the psi button. So it's simply second, 5, and it puts it into scientific notation for you. And you can see the answer then is 3.33 times 10 to the negative 5th liters. All right, folks, it's a little bit after 1 o'clock in the morning. I'm going to bed. Good night.